the stationary wave again. Let me share the. So you can see the PowerPoint. Okay, so everyone can see the PowerPoint. Just to double check.
Yes.
Okay, good, thanks. Okay, so halfway of stationary wave. Another 1 hour to finish it off. So string produce stationary wave, fundamental, first harmonic, second harmonic, third harmonic. Okay. So now we go into formulas now. How to find the frequencies. Okay. How to find the frequencies, how to work out the wavelengths. Okay, now we go to quantitative. So yes, if you use a string, you can use the, if your frequency is lower, you make a 1 loop, it's fundamental. This is 2 loop, 3 loops, and so 4 loops. So you rise the frequency, you get more number of loops. Okay. As I said, what? When frequency, sorry. As I said, what? When the frequency is raised, okay, and the frequency is raised, of course the wavelength get shorter. Wavelength get shorter with the speed is constant. Okay, so this is the 3 formulas you have to remember. So you see, when there is a fundamental one, okay, you have a fundamental one. Okay, so this is fundamental, okay, the fundamental appearance of fundamental frequency. The length from node to node, this node to node, how much? Node to node is, this is how many wavelength? This consider half wavelength, half wavelength. So V equals to F naught lambda. Okay, from here V equals to F lambda. V is the speed of sound, speed of wave. Sorry, not sound. This is the speed of the string. Speed of the wave in the string, on the string. And this F we put F0. F0 is a symbol for fundamental frequency. Fundamental frequency. And lambda. Okay, lambda is the one we get it from the length of the string. Here lambda is equals to 2L. 2L, right? As I say, half lambda is L. So lambda is actually what? Lambda is actually 2L. 2 times the length of the string is the lambda. Okay. So 2L, you put a 2L. So you get frequency for the fundamental. The frequency of the fundamental is depend to the speed of the wave in the string and depend to the length of the string. CV over 2L is the fundamental frequency. Okay, this formula you have to remember. Okay, you have to remember this formula. Okay, so the derivation also you have to know. Okay, so yeah. So when the frequency, the vibrator frequency is raised, when the frequency is raised, okay, when the frequency is raised, what happened? As I said, frequency is raised, the wavelength gets shorter. That's what has been shown here, manifested here. So now you have 2 loops. So if 2 loops, V equals to F1 lambda. F1 is the new frequency is formed. V is still the same because, as I told you, speed in the string is depend to what factor? Speed of the string, speed of the wave on the string is depend to the tension and the mass spinning length of the wire, which both we fixed, and both we fix it, so that the speed is constant. So speed is still V. F1 is the new frequency. Lambda now, we find a new lambda. Lambda new one is this. How many lambda is this? This is 1 lambda. One going up, and come down. This is actually 1 wavelength. 1 wavelength. So 1 wavelength is L. So lambda is L. So lambda we just replace with L. So F1 is VOL. So this is the new frequency. Okay, now you compare. Now you compare this F1 with F2, F0. F0 is V over 2L. F1 is V over L. V over L, how many times greater than the F0? So V over L, you divide by V over 2L, you get 2 F0. It's 2 F0. 2 F0. That means what? If the original frequency 50 Hertz means, okay, the following one will be 100 Hertz. It will appear at 100 Hertz. So because the frequency is double exactly from the fundamental, we call this as a second harmonic. This is a second harmonic. This is second harmonic. Okay, so this continues. This pattern is continuous. So you rise the frequency further, you get the 3 loop. This 3 loop is how many lambda? What is that? 3.5 lambda is L. So I think you can see this formula. 3.5 lambda is L. So therefore, L equals to what? 3/2 lambda is L. So lambda equals to what? Is 2/3 L. 2/3 L. So that's what we substitute here. So lambda is 2/3 L in terms of length. In exam, they won't give you lambda. They just give you the length of the string. From the length of the string, you have to work out the lambda by looking at the appearance. Okay, so 3L. So this F2. So make the F2 is 3V2L. 3V2L compared to F0, V/2L. 3V2L divided by V/2L. What do you get? You get 3F. So this is the third harmonic. This is the third harmonic. Okay, this is your third harmonic. So if this happens 50 Hertz, this happens 100 Hertz, this will happen at 150 Hertz, and so on. This will happen at 200 Hertz. Okay. So in this string, you have fundamental, first harmonic, second harmonic, third harmonic, and fourth harmonic in order. What is same for all of them? What factor is always same for all of them? The speed of the wave is always same on the string. Okay. Any question from this slide? Okay, can you understand? Okay, so this is the calculation part. Okay, you must link how wavelength linked to the length of the string. How the wavelength is linked to the length of the string, you have to work out. Okay. Okay, now. Okay, so that's about. That's for the string. Okay. Now we go to this open pipe pattern. We go to the closed pipe first. I just want to go for closed pipe. This is a closed pipe. Closed pipe. You see the end is closed with the water. So you take a tuning fork. Tuning fork produces a sound at a particular frequency. So the tuning fork produces sound. The sound go into this column and reflected produces a stationary wave. Okay, stationary wave. Okay. So now this is a closed pipe. Okay. So maximum amplitude always happen at the open edge. Maximum amplitude happens at the open edge. Why the maximum amplitude happens at the open edge? Because the particle in the open edge can easily oscillate because they are low pressure. Okay, easily can oscillate. So open end always forms antinode. It forms antinode. Antinode means what? Constructive or destructive interference? Always a constructive interference. Constructive interference happens. So open end always form constructive interference. This open end. Open end always form constructive interference. Cannot move at a closed end. Maximum amplitude at the open end. At a closed end here, you can imagine what? A particle at a closed end here, the particle here was trapped. It cannot go deep into the water because water as the border blocks it, and the particle above it also pushing it. So under high pressure, they can't really oscillate. So air cannot move at a closed end. So therefore they form a node. Node means destructive interference happens at the closed end. So yeah. So this is how the pattern going to look like. This is how the pattern going to try to draw the next harmonic. Okay, we're going to draw the next harmonic here. Okay, this is the important patterns you have to remember. Okay, so when the fundamental frequency is the lowest frequency. At the lower frequency, okay, the lowest frequency, when the frequency is the lowest, okay, when the frequency is the lowest, okay, we know that the wavelength should be the highest. Wavelength should be the highest. So this is the fundamental appearance. At the closed edge, it form a node. At the open edge, it form an antinode. So this is the pattern of the wave. This is the pattern of the wave. Okay, the particle at the node amplitude is 0. It does not oscillate, but particle at the antinode oscillate the most. It has the greatest amplitude. Okay, because it's a sound wave, it oscillates horizontally. The particles are oscillating horizontally. The oscillations amplitude getting smaller and smaller. Greatest at the open end. Greatest. It oscillates horizontally. Okay. So to refer to in a graph, the graph will be like this. This is the graph going to be like the graph in terms of what? In terms of what distance versus the displacement. The graph of amplitude, the displacement will be like this. That's what drawn here. Drawn here. Okay. Now tell me, this is how many wavelength? This is how many wavelength? Close by. From here to here, this is how many wavelength? This is how many wavelength? You see, just from the center, it go up to the peak. Then it can come down. Then it go another half cycle. So this is how many wavelength?
1/4.
1/4. Very good. This is a quarter wavelength. It's a quarter wavelength. So same thing repeats back as stationary, like a string last time. So the quarter wavelength is the length of the tube. The length of the tube, L. So L, quarter wavelength is L. So we can find the lambda of the wave produced inside in terms of the length of the tube is 4L. So that's what written. The lambda is 4L. Lambda is 4L. Okay. So once you know lambda 4L, now you can find the frequency. Frequency is what? Frequency is V over lambda. This is the fundamental frequency. So V, speed of sound. In exam, speed of sound will be given to you. Speed of sound is normally how much? Around 330 meter per second. Okay, speed of sound will be given. No need to remember. Wavelength here in terms of length, you have to know is 4L. Is 4L. Okay, this is the fundamental frequency. It's a fundamental frequency. Okay, or we call it as what? First harmonic. It's the first harmonic. Okay. Okay, next. So next, when the frequencies rise, you blow with a high pitch, what happened? This appearance, right, will be compressed. Tend to become like this. It will become like this. Okay. You see, this the quarter wavelength will be compressed to this. Okay. The entire thing will be compressed to inside until a loud sound won't appear. After you change from it here, loud sound won't appear until a nice antinode is formed at the open edge. That means node, antinode, another new antinode appears at the open edge, you listen a loud sound. And this is the following pattern. You now tell me, this pattern is how many wavelength? This pattern is how many wavelength? Going up, come down, and go further down. This is how many wavelength? This is from here to node is how many wavelength? Node to node is half wavelength. Then node to another antinode will be how many wavelength? Quarter wavelength. So altogether, how many wavelength? 3/4 wavelength. This is 3/4 wavelength. From up to down, node to node is half wavelength. So node to another antinode is quarter wavelength. So 3/4 wavelength. So 3/4 wavelength is the length of the tube now. Okay. Yeah, the lambda. So therefore, lambda is equals to what? Lambda equals to this all 403L. 403L. So now find the new frequency of this. The new frequency, the first frequency is what? V over the new lambda 1. So the V is still V, but the lambda is how much? 4/3 over L. 4/3L, but you will flip it. It's become 3/4 V over L. Okay. Now this is F1, new frequency. This F1, how many times greater than the fundamental? Fundamental is V over 4L. F1 is 3V over 4L. F1, how many times greater than the F0? 3/4VL, V over 4L. How many times is greater than this? So it will be 3 times. Okay, 3F0. 3F0. You try and see 3/4 V over L divided by V over 4L, you get 3F0. Okay, so this new frequency is 3 times greater than the first one. So therefore, this called as, there is a mistake. Can we call it as second harmonic? Can we call it second harmonic? You can't. It's not second harmonic. It's what actually? It's the third harmonic. Please correct the slide. There is a mistake here. This is not second harmonic. This is a third harmonic. Okay, third harmonic means what? The frequency is 3 times greater than the fundamental. Okay, Okay, now, so that's a mistake here. This is not second harmonic. Second harmonic means the frequency must be twice greater than the fundamental. This frequency is 3 times greater than the fundamental. Okay, can you correct for me the third one now? This one should be what harmonic? Now the frequency increase, the compression happen, then another antinode is formed at the edge. You will listen a loud sound. This is harmonic wavelength. Anyone? Check this harmonic wavelength. One loop half wavelength, another loop half one wavelength. This is quarter. So altogether how much? 5/4 lambda. That's lambda is equals to the length of the tube. So lambda is 4/5. So what is the new frequency here? F2. F2 is V over lambda. So it's going to be V over what? V over 4/5L. So this becomes 5/4BL. Therefore, this F2 how many times greater than the fundamental? V over 5/4BL divided by V over 4L. So it will be 5 times. 5 times of the fundamental. So what's the mistake here? It should not be third harmonic. It should be what? Anyone? It should be fifth harmonic. This is fifth harmonic. Okay. In exam, they'll ask you link the lambda equals to L. In exam, they'll ask you to draw this 3 pattern. Okay, this 3 pattern. Okay, remember this 3 pattern was formed by changing the frequency. The pitch has been changed. Pitch has been changed. In the lab, this can be done by using this setup. This is the setup we use. This is the setup we use. This is the air column here. This is the air column here. The wave going to form inside this column, the pattern. The pattern here, this 3 pattern going to form inside the tube vertically up. So the tube is, let's say the tube is here. The fundamental means we imagine that the sound produced like this. Okay, produced like this. The closed edge of the water forms node, and the open edge forms antinode. Okay. In exam, the open edge, why it forms antinode? Because that's the lowest pressure. The pressure is the lowest. Pressure lowest, the particle can oscillate maximum amplitude. Therefore, it's a constructive interference. Constructive interference. Note, it has a high pressure, very high pressure, because the water blocks it from moving. The particle on top of the particle at the corner also blocking it. So it will be like high pressure. It's unable to move. So it forms a node. Any question from this slide?
I have a question. In the experiment, how do we know we have reached the first, third, and fifth harmonic? Like, how do we visually see it, like to record?
Okay, so first you have to make sure after you you put the harmonic, make sure the water level here is up to high here, full first. Okay, then what you just bring this object, right? This corner, you just bring it down. You bring it up. Okay, so when you bring it up at the beginning, when it's fully water, completely water, this level will be on top here. You have to be on top here. Okay, you want to bring this down. You bring this is a manometer. It's a manometer. Yes. The level have to be the same. So you bring this down. The level water here will go down. Go down. You listen first. There will be suddenly a loud sound will appear.
Oh, so we listen to it.
Suddenly a loud sound will appear. When a loud sound appears, stationary waves form. The first loud sound from the top to the down when the level is going down. That's your fundamental. Okay. Then after that, you keep on reducing it. Suddenly the loud sound disappear. Then when come to F1, the following frequencies, again loud sound will appear. When loud sound appear means stationary wave is already formed. Okay. Okay. I hope we can get into the lab to do this experiment. Okay. Hopefully next month, see how it works. Okay. So yeah. Any other questions? So you have to remember these formulas. In the exam, they won't give you the formulas. They ask you to draw this appearance. Okay. So for a closed pipe, the closed edge always form what? Node. The open edge always form antinode. The largest wavelength can be is the quarter wavelength. Okay, the quarter wavelength. Quarter wavelength led to the fundamental frequency. Okay, any other questions from this slide? No questions. So remember, the pattern appearance is different from the string. String and closed pipe, the pattern is different. Closed pipe, what is the pattern looks like? The earlier one. Sorry, I go back. Okay, this is the pattern for. Sorry, I go to the earlier one. Where is it? This three. This three is the pattern for the what do you call, for the string. You see, like this loop. Age are nodes, center is antinode. Age always nodes. Okay, but for a closed pipe, close end is node, open end is antinode. Okay. So now let's go back to this. This is open pipe. Both ends are open. Still, they found stationary waves looks like forming. Okay, this is the pattern going to looks like for open pipe. Okay, we got musical instrument which has pipe. Okay, like pipes. We can produce a sound. Okay, so when you blow here, so this is the loud sound appears. Open edge always form no antinode because it's low pressure. So in this case, if you have a pipe, the longest wavelength can produce is this is antinode, this is antinode. So the longest wavelength produced is like this. Tell me, this is how many wavelength? From up to down, how many wavelength it is? From up to down. This is how many wavelength? You see, another quarter will be outside here to make one wavelength. Another quarter is outside here. Another quarter is outside here. So the center is how many wavelength? From crest to truth. Crest to truth. So this is how many wavelength? This is half wavelength. This is half wavelength. So this is half wave. Half wave. They put a half wave. Half wavelength. So the length of the string, let's the length of the pipe, let's say L. So we said what? Half lambda equals to L. So what is lambda? It's 2L. It's 2L. So then what is the fundamental frequency will be? V over lambda, but V is speed of sound. Lambda in this case is 2L. So this is the fundamental frequency formula for an open pipe. Okay, for an open pipe. Remember this pattern. Pattern, open edge always form antinode. Okay. So then you increase the frequency, you won't listen to the loud sound. Suddenly loud sound will appear. When this pattern, the X pattern is compressed. You see this pattern, the X like this, the crest and trough, it has been compressed. It will be compressed until another node is formed. Another node is formed, then you listen to a loud sound. So this is the following harmonic. How many wavelengths is this? This how many wavelength? So like crest to crest, how many wavelength? This is one wavelength, exactly one wavelength. So tell me, one wavelength. So lambda equals to L. So the new frequency F1 is what? V over lambda. So it's going to be V over L. Okay. So F1 how many times bigger than the F0? F0 is V over 2L. F1 is V over L. So F1 is actually 2F0 twice. That's why it's written here. Okay. The F1 is 2F0. It's 2F0. So we call it as, what harmonic is this? This is second harmonic. This second harmonic. Second harmonic. 2 times the frequency greater than the fundamental. Okay. So the third one continues. Okay. Now this one wavelength will be compressed, will compress until you get another antinode. It means every time compress, another X shape like getting into the picture. Like X shape, you see, like a half wavelength getting into the tube, half wavelength getting into the tube. So here they found that the frequency is just rising. So this is third harmonic, this is fourth harmonic, and it continues. This is open pipe. Okay, open pipe, the formula is similar to string. Open pipe or closed pipe, the formula is similar to string. The formulas similar to string. The open pipe. The open pipe is similar to string. String also got what? String also got first harmonic, second harmonic, third harmonic. Okay. Open pipe also got first harmonic, second harmonic, third harmonic. But only the closed pipe, the even number of harmonic is missing. Got first harmonic, then don't have second harmonic, only have third harmonic. Okay, so if you use open closed pipe, you only have third harmonic. That means the fundamental frequency is 500 hertz, means at 2 times of the frequency. Let's say 500 hertz is the fundamental, 2 times of the frequency, 1000 hertz, you won't get loud sound for a closed pipe. Closed pipe only have third harmonic. That means the frequency you must use to get a third harmonic, you must rise the frequency 3 times of the fundamental. Okay, so the first 3 patterns you have to remember. Okay, 3 patterns to remember. Okay, any questions from here? Okay, these are the 3 patterns you have to know. For string, closed pipe, open pipe, the pattern of stationary wave forms inside, you have to know. And how many wavelength linked to the length, you have to know. Okay, any questions? So hope you can understand. Okay, when we do questions, maybe we have get a better understanding. Okay, this experiment is quite unique. This experiment, they use the same tuning fork, they use the same tuning fork. So you use the same tuning fork. So in this case, do they change the frequency? Do they change the frequency? The frequency of the sound, they never change. They only rise the pipe higher. When they rise the pipe higher, you listen a loud sound when it's like a quarter wavelength. When you rise the pipe higher, until another half wavelength forms inside, you listen a loud sound. So this is why it's so unique. Here the frequency doesn't change. They use the same frequency because they use the same tuning fork. Only the another half wavelength has been appeared here. So for these 2 appearance, the wavelength does not change. The wavelength is still the same length. Okay, the same length. Because the tuning fork, we use the same tuning fork. Okay. Okay. So before we go to this, let me do some questions first to understand. We go to the passive questions about stationary wave. Okay, so now we try to strengthen the idea what you learn. Okay. Okay. So first page 1, question 29. What is the answer? Everyone give a try. Okay, give you 1 minute. You can WhatsApp me the answer. Okay, so anyone can give me the answer? Okay, I got answer D, or C and D. So C, one of you said C, one of you said D, C or D. Okay, it's I'm getting more answers D. So 2 of you say C, 2 of you say D. Okay, so let's say it's C or D. Okay, so this is first you must check. First, when you do the questions here, first you must check, is it a closed pipe, open pipe, or a string? That's the main thing. So this case is a stationary wave adjacent, or this is, they said, node to node is 1.5 meters. That means from node to node, the length is found to be 1.5 meter. Node to node, how many wavelength? Is half wavelength. So half wavelength is 1.5 meter. This is what you need to conclude. Half wavelength is 1.5 meter. So wavelength is how much? Is 3 meter. Node to node is half wavelength. Okay. So what is the speed of the progressive wave? So V equals to F lambda. So F is 300 and lambda is 3. So it's 900 meter per second. Yes, it's 900. So it should be D. Yeah, the answer is D. Okay, do you understand? Can, so node to node is half wavelength. Okay, node to node is half wavelength. Okay, let's move on. More questions? Okay, remember, remember, is it a string, closed pipe, open pipe? Because the pattern is different. Okay, another one question is, okay, this one. 24, what's the answer? This is page 6. So this is straightforward, right? X and Y is node or antinode? X and Y are two adjacent antinodes. So antinodes to antinodes, what are the wavelength? Antinodes to antinodes, antinodes to antinodes also is going to be half wavelength. It's the distance, but it's distance. So therefore, half wavelength. Half wavelength. Yes, your friend, you are also giving saying this T. It's T. So antinode to antinode half wavelength, node to node is half wavelength. Whether it's closed pipe, open pipe, or string, node to node, antinode to antinode, always half wavelength. So D. Okay. November 3, what page is this? This is page 8, 24. You mean the answer? Oh, sorry. But that's now. So is it D? One of you saying D. So stationary wave sound as a series of nodes, the distance between the first and 6 nodes. We better draw the diagram. First from first to 6th node is 30 centimeter apart. What is the wavelength of the sound wave? So first, second, third, fourth, fifth, sixth. This is the first node. This is the second node. This is the third. This is the fourth. This is the fifth. This is the sixth. Yeah, okay. So from first to sixth node is found to be 30 centimeter. So what is the wavelength? Okay, many of you say D. Is it 12 centimeter? Yes, you see. How many wavelength is 30 centimeter? This is 2 loops is 1 wavelength. It's 1 wavelength. This is another 1 wavelength. This is half wavelength. So conclusion is 2.5 wavelength is 30 centimeter. So you get the wavelength. Wavelength is 30 over 2.5. 2.5. You get 12, is it? Yeah, 12. Yeah. So D is the answer. So first to 6 node is actually 2.5 wavelength is 30 centimeter. That's what you conclude. You get the wavelength. Okay. Good. Okay, now. Okay, more questions. Okay, so yeah. What page is this? This is question 14, page 14, question 25. Give me the answer. Need the answer. Come on. Okay, so a stationary sound wave is set up along a line joining the two loudspeaker. Which measurement is sufficient on its own to enable you to reduce the wavelength of the wave? What measurement you need to take to get the wavelength of the waveforms in between stationary wave? The distance between two loudspeaker, the distance between two adjacent antennas, the distance between two loudspeaker. Okay, so I get a mixed answer. Many of you say C, one of you said it's B, but many say C, B or C. Okay, distance between two loudspeaker, we don't know. You find this distance of the two loudspeaker. We're not sure how many loops it forms in between. So I think pointless to find the distance between two loudspeaker. But if you know the adjacent two antennas, one antenna to antenna, if you know the distance, we definitely know it's half wavelength. So we times 2, we can get the wavelength. So the best choice is C. Okay, C, antennas. Okay, distance between two antennas can give us the wavelength very easily. Okay, B, two loudspeakers. We don't know how many loops forms inside, so you can't get the wavelength. So C is the best answer. Okay, next. Okay, this is next. Yeah, 27. The same page. The following question. The diagram represents a stationary wave. Okay, so stationary wave. Okay, so I got the answers. C. C. Yeah. What is the represented point P? P is a node, of course. And what is the distance of X? Is one wavelength. It's one wavelength. It's a straightforward question. Not that challenging one. Okay, this one. Okay, 27. This is page 16. Okay, this question is about microwave. Microwave also forms stationary waves. Okay, get me the answer for this, 27. Okay, so small microwave receiver is moved steadily from T to S. Receives signal of alternate maxima and minima. Maxima is maximum intensity means antenna. Minima means is node. Okay. Okay. So the distance between successive maxima is 15. Okay. So successive maxima means distance between two antinode. Antinode, let's say here happens antinode and here antinode, they say separated by a distance of 15 mm. So what is the frequency of the microwave? So frequency is what? V over lambda. Okay. So lambda how much? 15 mm, how many lambda? 15 mm is half lambda. Antinode to antinode is half lambda, right? So lambda how much? Lambda is 30 mm. 30 mm. So lambda here is 30 times 10 power of -3. We put it in meter. Speed. Speed of microwave is how much? Microwave is electromagnetic wave. So speed is what? 3 times 10 to the power of 8. You need to know. Okay, speed of light you have to know. They won't give you. They expect you to know. So 3 times 10 to the power of 8 is the speed. So you get your frequency. So what do you get? 0.1 times 10 to the power of this what? 11. So 1 times 10 to the power of 12. 1 10 to the power of 10. Okay. 1 times 10 to the power of 10. So I think you get C. Okay, so all of you get C. Any questions? You don't understand here? Okay. So yeah, should be C, yeah. The trap here is the speed of light. You have to know, so you have to put that. Okay, any questions so far? Okay, you know, I just want to tell you this. You know, microwave, the type of wave is, let's say I draw a microwave. In a microwave oven, the type of wave forms inside the microwave oven is a stationary wave of microwave. The microwave wave is traveling, and it was reflected, and it forms a stationary wave inside the microwave in all direction. Too many reflections, so forms a stationary wave inside. Okay, the point where the node happens, where the antinode happens, is constructive, and the node happens. So remember, the type of wave happens inside the microwave oven is a stationary wave. It's a stationary wave. Okay, now tell me, why the food need to be rotated? Why the food inside the stationary wave, when you on, the food will start to rotate? Why it need to be rotated? Anyone? Why the food need to be rotated in the microwave? If you never rotate the food inside the microwave, what will happen to the food?
Only one side will be.
Yeah, good. You are close.
Only one side of the, no, like one area of, not one area, like one lateral area of the food will only be cooked like that.
Very good. Yeah. So the food is there. Let's say the pizza. Put it into the microwave. Because the stationary wave is forming inside on the food. The point where the antinode happens, that's the point where the heating happens. Heating happens at antinode. No heating happens at the node. So antinode, all the point where the antinode forms on the food, that's where the burning happens. Very, what do you call, aggressively. So if you need to rotate the food. If you never rotate the food, only the particle point will be overcooked. The other won't be cooked. So therefore, you need to rotate it so that the antinode happens in everywhere. So even heating happens. That's why it need to be rotated. So remember, the type of wave form in the stationary wave, I mean the microwave oven is a stationary wave. It's a stationary wave. Okay, so the question is like this. Okay, it's like this. You go and give a try. Okay, now you have to go to the last point, this part. Okay, this is very important. This is the differences between progressive wave and stationary wave. Okay, so look at the first point, amplitude. Okay, amplitude. First is stationary wave, the other one is progressive wave. You see, amplitude. For progressive wave, all the particles of the waves has the same amplitude. Do you agree? Let's say if it's a progressive wave, A, B, and C, three particles, eventually will reach the top. So all of them will have the same amplitude or different amplitude. All the particles on the path will have the same amplitude. They will have the same amplitude in progressive wave. But in stationary wave, is all particle has the same amplitude? Do they have the same amplitude? You see the stationary wave, I go for the two loop one. The particle A and particle B, the particle A, so you got a particle A, you got a particle B, you got a particle C. Particle A only oscillate here now. This is the oscillation of the particle A. Particle B is from here to here, up and down. And particle C is somewhere here. And particle D at the node don't have any amplitude at all. So tell me, every particle in a loop, do they have same amplitude? They have a variety of amplitude. Varies according to the position. Okay, the one at the antinode will have the greatest amplitude. Okay, the amplitude said to be maximum can go up to 2A. Why it's 2A? Anyone, why it's 2A? Because the stationary wave is formed by who? Two incident wave at the background. Okay, if one incident wave has an amplitude of A, another reflected wave also has an amplitude A. When they superpose at the antinode, A become how many A? Become 2A. So the amplitude from 0 will reach up to 2A at the antinode. Node 0, the amplitude at antinode will be 2A. because incident wave has amplitude AA. So do you understand about amplitude, the differences? This is the difference between stationary and progressive wave. Progressive wave, all particle has the same amplitude, but stationary wave, all particle has a different amplitude, range from 0 to 2A. The nth node has the highest amplitude. Okay, so you got idea. Okay, next, I go to the energy first, the lowest one. Okay, if the question asking for one difference, what is the difference between progressive and stationary wave? I think the best answer you can give is about the energy. This is the first thing you can talk about, energy. Okay, what is about energy? I think I already told you. Stationary wave is a type of wave that energy is within the wave, is localized. Energy is not transferred. Okay, for progressive wave, energy has been transferred from one point to another. Energy is transferred from one point to another. So this is the main difference of stationary wave and progressive wave. If question asks, what is one difference between stationary and progressive wave? The expected answer I like to see is about energy. Energy in the stationary wave is localized, never transferred. Progressive wave is transferred from one point to another. Okay. And the second one, waveform. Waveform, or we can say the wavefront, the wavefront. For a stationary wave, the wavefront does not advance. As I said, just now the water wave, the crest, at the point where the nth node happens, does not move forward, does not advance. For a progressive wave, the wavefront will move forward. Okay, the pattern will move forward. Move forward. Okay, it just move forward. Okay, so that's the second one. Okay, now the third one, phase. This is very important. Okay, you must understand this phase again. For progressive wave, all particles within a one wavelength have a different phase, right? So let's say you have a wave like this progressive wave. If I choose one point A, point B, find the phase difference. You can find the phase difference. What is the formula? X over lambda times 2 pi. Or you can use what? Period over T over period times 2 pi. You get the phase difference. As long as they have X, they have phase difference in progressive wave. Okay. Don't ever use these two formulas for stationary wave. Stationary wave, phase difference, you can't use these two formulas. These two formulas only to find phase difference for what? Only for progressive wave. Remember, the X over lambda times 2 pi, T over period times 2 pi only works for progressive wave. For stationary wave, the phase difference is very easy. No need to calculate. Why? You see, for the phase, the first loop and the second loop. First loop, A and B. Okay, I draw A and B. A and B. Okay, if A goes down means B also will goes down, right? They come to the bottom. When A start to move up means, and the A start to move up means B also will start to move up. So A and B within the first loop, the entire first loop always move in the same direction. Okay, so all the particles in the first loop are said to be in phase. It's said to be what? In phase. Okay, so that has been recorded here. All particles between the two adjacent nodes are in phase. All of them are in phase. They always move in the same direction. Okay, they always move in the same direction. What is the phase difference between one particle on the first loop and the one particle from the second loop? Anyone? Yeah, this part, I think, let me show the animation is better. Go to the animation. I think this works. Okay, talking about a phase. Okay, I'm just talking about a phase. This is a stationary wave. You see the first loop. This is the first loop. Let's say this is the first loop. In the first loop, you see particle here A. Yeah, particle here A is moving from here to here. Particle B is here. You see all the particles in the first loop. When they move up means all of them move up. When come down means all of them will come down. So first loop, all the particles are in phase. Tell me what is the phase difference between the first loop and the second loop. This is the second loop. This is the second loop. You see? And the first loop going down means second loop going where? Second loop going where? So second loop going up. So and in the stationary wave, and the first loop going down means the second loop is going up. Okay? And the first loop is down, second loop is up, and the first loop is going up means the second loop is start to move down, right? You see the loops, first and the second loop. So what is the phase difference between the one particle in the first loop and another particle in the second loop? They always travel in opposite direction. Yeah. If they travel in opposite direction, the phase difference is how much?
180.
180 degrees. Yes, it's 180 degrees. Or we can say pi radian. Pi radian. Okay. So two particles in adjacent loop. Let's say there is a phase, there is a stationary wave. They say this is the first particle, this is the second particle, and they say it's a stationary wave. If it's in an adjacent loop, what is the phase difference between A and B? The phase difference is 180 degrees or pi radian. They always move in opposite direction. If A and C, two particles in the same loop, if I ask what is the phase difference between A and C, then it should be 0 radian, or you can say 0 degrees. And they are in phase. A and C is in phase, but only if it's a stationary wave. Okay. If it's a progressive wave, what is the phase difference between AC? You have to use the formula x over lambda times 2 pi. Okay, remember again, don't ever use this formula for stationary wave. Stationary wave only got two phase difference, either 0 if they are same loop, or 180 if they are in a adjacent loops. They are adjacent loops. Okay, now tell me, what is the phase difference between stationary wave, okay, for the particle A and particle C here? Anyone? One particle at first loop, another particle in the third loop. First loop and third loop, what is the phase difference? Anyone?
0.
Okay, again 0. First loop, third loop are also in phase. First loop goes down, third loop also goes down. They are in phase. Okay, good. So this is your phase difference. Phase difference. Okay, so yeah, look at the phase difference. Number 3, phase difference. So phase difference, all particles between the two adjacent nodes are in phase. This is for stationary wave. For all particles, wavelength has a different phase. Yes. So this is the third differences. Fourth one, wavelength times 2 of the pair of adjacent nodes. Yeah, node to node is half wavelength. You times 2, you get one full wavelength. Times 2 of the distance between the node to node is one wavelength for stationary wave. For progressive wave, this is the definition for wavelength. Distance between two adjacent particles which are same phase. Okay, so you have a wave. This distance between two crests. Two crests means same phase. Two particles which are in the same phase is called wavelength. My wavelength for progressive wave. Frequency instead of phase difference, frequency is a similarity. All of them is a similarity. Okay. In a stationary wave, all particle has the same period. Time taken for the particle A to go down and up is the same as particle B to go down and up. So they have the same period. So therefore, their frequency is the same. So the frequency is same for all the particles. Same thing goes for the for the progressive also. All the particles has the same frequency. Okay, so these are the differences, comparison between these two. Okay, so you have to remember these differences. Okay, if they ask the main differences, talk about energy. Any questions from here? Okay, this is the fact to remember. Please memorize this fact about stationary wave and progressive wave differences. So any questions so far? So we're done with stationary waves already. Okay, part 1. Okay, so as usual, if you don't have questions, then we can stop here. Okay, class. So today's class, you learn a lot of new stuff. Okay, so something new. I know it's original texting, so go back, take your time later, and recall it back. Show the video. Okay. Okay. So your semester exam consists of 10 topics. This is the 9th topic. We have another 1 topic to go, electric field. then we stop. Okay, then we go for the, hope we get 1 or 2 lessons to do semester exam. Okay, those who are did a revision, you can try the semester papers below your times. There is semester papers, you can give a try also, that one. Okay, so I stop here. See you tomorrow.